Okay, next I'm going to talk about acids and bases. Here's an example of an acid, HCl. And we probably all know at this point that acids are proton donors. And these are the form also known as Bronsted acids. These are proton donors. Bases, an example is sodium hydroxide. Bases are defined as proton acceptors. And these happen to be examples of a strong acid and a strong base. So when HCl gets dissolved into water, it dissociates completely, because it's a strong acid, into aqueous H+ and aqueous chloride. Sodium hydroxide dissociates into Na+ aqueous and OH- aqueous. And that OH with the negative charge is able to accept a proton. And remember, a proton is H+. Some of my equations did not translate well. So pH is defined as the negative log base 10 of the concentration of H+ in solution. And the pH scale goes from 1 to 14. If the pH is 7, we say that it is neutral. And at pH 7, neutral pH, the concentration of H+ is equal to the concentration of OH-. Those brackets mean OH-. And also it's worth pointing out that this is a logarithmic scale. So that means if you change the pH by 1 unit, there's actually a 10-fold increase or decrease in the concentration of H+. Solutions that are acidic have a pH below 7, and they have a higher concentration of H+ versus OH-. Basic solutions have a pH greater than 7, and their concentration of hydroxide is greater than the concentration of H+. Remember, strong acids and bases completely dissociate in water. I showed that on the previous slide. Weak acids, which are incredibly important in biochemistry, do not completely dissociate. And so because of that, they are in equilibrium. And we can, in a general form, denote a weak acid as HA, or any acid. But in this case, because I have an equilibrium arrow, this is a weak acid, it dissociates into H+ and leaves behind A-, known as the conjugate base. And equilibrium constants are defined as the product of products over reactants. So it's the concentrations of products divided by the concentrations of reactants. If you came up through Chem 100 or 152, you may not have seen equilibrium expressions, but that's okay because we're not going to use them very much. But we are going to use a rearrangement of them. So this equilibrium constant, that's this number here, that is a value for a particular weak acid. And the bigger that number, the stronger the acid. And Ka's generally have large negative exponents. So, and actually the proper way to write this equilibrium expression is you take a weak acid, dissolve it in water, and what happens is this H becomes part of the water to make hydronium. And then what's left behind is A-. And hydronium is the conjugate acid of water, and A- is the conjugate base of HA. I'm going to fill in some things here. Water is a weak acid because in solution, water, I'll write this out so it's a little bit easier to see, can dissociate into OH minus and H plus. And with neutral water, for every time one breaks down, you get one OH minus, one H plus, so that means their concentrations are the same. This is in equilibrium, so it has an equilibrium constant. That equilibrium constant has a special name, and that is Kw. So at all times in any aqueous solution, the concentration of the H plus multiplied by the concentration of hydroxide in molar form equals 10 to the minus 4. That is always true. Concentration of H plus times concentration of hydroxide equals 10 to the minus 14 molar. It turns out when the two concentrations are the same, we have neutral pH. And like I said before, when H plus is greater than hydroxide, then we have an acidic solution. When hydroxide is greater in concentration than H plus, then we have a basic solution. So a buffer is a weak acid and a conjugate base pair. You must have significant quantities of both. So here below is an example of a weak acid. And this, as drawn, is actually acetic acid. And this is the HA form of this weak acid. If you also have significant amounts of acetate, that's the acetic acid minus the H plus, that would be our A minus. If you have significant amounts of both of these, then you have a buffer. And notice the only difference between these two species is the loss of an H plus. It's always the same. And the species that has the H is the weak acid. The species that does not have, that has fewer H's, is always going to be the base. Now in biochemistry, it turns out a lot of times the weak acid base combinations we study involve nitrogen. So this is tris base here. And notice this ammonium group. So this is actually HA. Some people would call this BH plus because it's positively formed and it's a weak base. The other form of this is going to look exactly the same, except for it's going to have one less hydrogen on the nitrogen. So this is A minus. And if people are using the B format, they would call that B. They only differ by the loss of H plus or the addition of it if you're going in the opposite direction. Okay, so which one of these is A minus? So you might want to pause the recording for a second and think about it. Is it A or B? A minus. Okay, I'm going to do the answer now. So this is acetate. This is acetic acid. And they only differ by that H plus. Always the form that has the extra H is HA. So this is A minus. Which one of these is HA? Again, you might want to pause. Think about it. Which one has more hydrogens? Okay, I'm going to give the answer now. And among these two species, or between these two species, B is the one that has more H's, and it's right here. Okay. In general, chemists tend to talk about equilibrium with equilibrium constants, these Ka values. In the context of acids and bases, weak acids and weak bases, there's a number that is a bit more useful directly, and that is called the pKa. The pKa is defined as minus the log of Ka. And the smaller the pKa value, the stronger the acid. And it's worth pointing out that pKa, just like pH, goes from 1 to 14. So something that has a pKa of 2 is a relatively strong weak acid. Something that has a pKa of 9 is actually considered a weak base. So it's a poor acid. And let me just say also that the pKa is defined, the other definition it has is it is the pH where the concentration of HA is equal to the concentration of A minus. And we're used to talking about pH when we think of, our frame of reference is pH 7, right? At pH 7, the concentration of OH minus is equal to the concentration of H plus. In acidic solutions, the concentration of H plus is greater than the concentration of OH minus. And then the reverse is true for basic solutions. But what I want you to think about when you're talking about weak acids and weak bases is instead our frame of reference now becomes the pKa. And I'm going to show you the relationships between, and the pKa is used to describe the relationship between HA and A minus, right? Not OH and H plus as much. It's a convenient way to gauge the strength of a weak acid. Okay, and here's a list of buffers. This is just something you look up, right? Not something that you memorize. But I like this table because it shows the name of a buffer, and it shows the acid form and the base form. And then it gives you the equilibrium constant for their dissociation, that Ka reaction. And this equilibrium constant, it's always the same. It's going to be generically HA plus H2O is in equilibrium with H3O plus and A minus. And the equilibrium constant is defined like any equilibrium constant. Concentration of products divided by concentration of reactants. Now notice this column here. This is where biochemists look because this is the pKa. It turns out that buffers function most effectively when they are within 1 pH unit of their pKa. So say I wanted to do an experiment at pH 3.3. Well, then I need to find a buffer with a pKa in that range. And if I look down the list, I see this one here is at 3.4, and it's malic acid, right? So malic acid has a carboxylic acid here and another one here. This is the HA form. This is the A minus form. One of the carboxylic acids is lost in H plus, and its pKa is about 3.4. And so that means that if I want to do an experiment at 3.3, this is a good buffer to choose. And it would be good roughly from 2.4 to 4.4 is the pH range. You want to go plus minus 1 pH unit. And so you would consult a table like this to decide which buffer you would want to use. There's other factors too as well, like there can be chemical interference, but that's of primary concern is to make sure that it will work in the pH range that you are interested in doing your experiment. Okay, I'm going to skip that.